Hello my dear children, we will speak with us today about the role of the salt bridge in the galvanic cell. The role of the salt bridge in the galvanic cell: first, it connects between the two solutions of the two half cells indirectly. The salt bridge connects between the two solutions, the solution of the anode half cell and the solution of the cathode half cell. So as we have mentioned before and explained it thoroughly, neutralizing the excess cations and anions formed in the two solutions because of the oxidation reduction reaction. So it connects between the two solutions, the cathode half cell solution and the anode half cell solution, indirectly, and also neutralizing the excess ions in the anode half cell and the excess ions in the cathode half cell. Okay, this is the first thing. So we'll take some questions about this. The opposite diagram illustrates the galvanic cell. So what happens during this operation of this cell? We speak in generally. Magnesium is more active than copper. Magnesium loses electrons. It is oxidized easily. Copper acquires electron. So copper acquires electron and magnesium release electrons. So magnesium half cell is the anode, which is exposed to oxidation, and cathode half cell is the copper. So what happens? Magnesium in the plate, magnesium metal, elemental metal or elemental atom, oxidized and goes dissolved in the solution to be magnesium positive 2. In the cathode half cell here, we see that the copper ions inside the copper solution reduced and deposited on the copper sheet in the cathode electrode. So in this case, magnesium ion increase here and attracts nitrate ion, negative ions, and here copper reduced and be deposited on the copper electrode. So here sulfate anion will be in excess. So here magnesium positive 2 excess, and here sulfate ion increases the normal level. So in the salt bridge, nitrate ion here go to the anode half cell to neutralize excess magnesium ions. Here potassium go to the cathode half cell to neutralize the excess sulfate ion. So what happened in this cell? Nitrate ions move towards the copper half cell. No, nitrate will go to the anode half cell to neutralize excess magnesium, which is oxidized. Okay, copper copper positive 2 ions move toward the salt bridge. No, copper here in the salt solution, in this solution, will be reduced and precipitated in the copper electrode. So it is wrong also. See, magnesium positive 2 ions move towards the salt bridge. Yes, magnesium ions positive 2, or magnesium atom oxidized into magnesium ion positive 2 and go toward the salt bridge to be neutralized by the nitrate ion. Okay, so the correct one here is C. Magnesium ions move towards the salt bridge. Another example. What happens to the reading of the voltmeter connected to the galvanic cell when the salt bridge is removed from it after a period of time of operation? So the salt bridge neutralize excess ions in the cathode solution and the excess ions in the anode solution, and keep no potential difference between the two solutions. if we remove the salt bridge which connects indirectly between the cathode half cell and the anode half cell, what will happen? The electric current will decrease gradually as the result of accumulation of the ions, of the positive ions in the anode half cell and the negative ion in the cathode half cell. So the electric current will decrease until it reaches 0, and the correct answer here is A. It decreases until it reaches 0. How to calculate the electromotive force EMF of the galvanic cell? There is some 3 forms of the same law which represent the calculating of electromotive cell. Okay, so the electromotive cell of any galvanic cell can be calculated by one of the following relations. Indeed, it is only one relation, but it is a different form. There are 3 different forms of this relation. It may be calculated by the standard oxidation potential of the anode plus the standard reduction potential of the cathode. We know that what really happens in the anode is oxidation, and what really happens in the cathode is reduction. So the standard oxidation which happens in the anode plus the standard reduction potential which happens really in the cathode, the summation of both of them gives the whole potential difference, or the whole potential of the cell. Second, it may be represented by or calculated from the reduction potential which happens in the cathode minus the reduction potential in the anode. What really happens in the anode is an oxidation. So if we want to calculate the reduction of the anode, we have to put minus sign. So the electromotive force here, in this case, if we want to calculate it according to the reduction potentials, it is the reduction potential in the cathode minus the reduction potential of the anode. Or it can be calculated from the oxidation potential of the anode minus the oxidation potential of the cathode. So what really happened in the anode? It is oxidation, so it is written first. What happened in the cathode? It is reduction. So if we want to calculate the electromotive force by the reduction values of the anode and the cathode, we have to make the oxidation potential, standard oxidation potential of the anode first minus the oxidation potential or standard oxidation potential of the cathode. And there is an information, very important information, which is the oxidation potential or standard oxidation potential of the electrode equals minus the standard reduction potential of the same electrode. So here we have to know that the electrons, application of this, to distinguish between the oxidation potential and the reduction potential. Here it is reduction potential because the element positive ion takes 2 electrons, so its oxidation state reduced from positive 2 here into 0. So this is a reduction potential which equals minus 0.76 volt. And here is oxidation potential. The second process, zinc 0 solid release electron and be oxidized in the form of ion, zinc positive 2 ions. So this is an oxidation potential which equals positive 0.76. So we see here the reduction potential of the zinc atom, of the zinc element, minus 0.76, and the oxidation potential of the same electrode, positive 0.76. So the oxidation potential equals minus the reduction potential of the same electrode. Here copper positive 2 reduced with 2 electrons to give copper 0 solid, and this is the reduction potential of it, positive 0.34 volt. Copper here in the second equation, copper 0 solid oxidized leaves 2 electrons and is oxidized into copper positive 2 and dissolved in the solution. So this is an oxidation potential of copper equals minus 0.34 volt. So what happened here? The oxidation of copper has negative the same value of the reduction of copper. So the reduction of copper here, copper reduced, the reduction potential of it is positive 0.34, and the oxidation potential of the same electrode negative the value of the reduction potential of the same electrode. So how can we calculate or solve problems concerning calculating the electromotive force here in this curriculum? So solving the problems of electromotive force, including knowing that the electrode which has higher potential, oxidation potential, is the anode, and the electrode with higher reduction potential is the cathode. So it is a very critical point. You have to concentrate on the problem. When it is given to you the value of oxidation, you have to know what is who is the oxidation potential higher. The higher oxidation potential of the two electrode, it refers to the anode. It refers to the anode half cell. And also you have to see if the value of the reduction process or the reduction potential is given to you, you have to know the higher reduction potential of whom is higher. The higher reduction potential refers to the cathode half cell. It's a very critical point to solve the problem. So the higher oxidation potential refers to the anode, and the higher reduction potential refers to the cathode. Okay, we will take the first example. Calculate the electromotive force of a Daniell cell, knowing that the standard potential shown in the table. So the oxidation potential of zinc is higher than the oxidation potential of copper. So zinc refers to the anode, and the reduction potential of copper on the other hand is higher than the reduction potential of zinc. So copper is the cathode in this case. So zinc oxidation potential is higher than copper, so it is anode in this Daniell cell, in Daniell cell, and here the reduction potential of copper is higher than the reduction potential of zinc, and it refers to the copper as a cathode. So we have three ways or three relations, as we have mentioned before, to calculate the standard the electromotive force of this cell. The oxidation potential of the anode half cell plus the oxidation potential of the cathode half cell, or the oxidation potential of the anode half cell minus the oxidation potential of the cathode half cell, or it is the reduction potential of the cathode half cell minus the reduction potential of the anode half cell. So the first answer, or the first way to calculate this electromotive force, is the standard oxidation potential of zinc electrode or the anode plus the standard reduction potential of the cathode. The standard oxidation potential of zinc 0 plus the standard reduction of copper positive 2, it equals 0.76. It equals positive 0.76 the oxidation potential of zinc plus positive 0.34, which is the reduction potential of the cathode. It may be expressed like this. Another way to express it, the reduction potential of the cathode minus the reduction potential of the anode. So the reduction potential of copper positive 2 minus the reduction potential of zinc positive 2, which is reduced into zinc 0 solid. So positive 0.34, which is the reduction of cathode, minus the negative or minus 0.76, which is the reduction potential of the anode, 1.1 also. We can calculate it by the oxidation potential of the anode minus the oxidation potential of the cathode. So the oxidation potential of zinc minus the oxidation potential of copper 0, which is oxidized into copper positive 2. So 0.76 minus 0.34, which gives 1.1, in all cases 1.1. Here we have to notice that the electromotive value of this galvanic cell or of any galvanic cell is positive. Positive sign here means that the oxidation reduction reaction occurring spontaneously. So positive means spontaneous. Okay, we have to answer these questions to understand more what happened or how to calculate the oxidation potential, the electromotive force of any galvanic cell. So galvanic cell consists of tin, which is oxidized into positive 2, tin positive 2, and silver from 0 to positive 1 aqueous solution. So the standard reduction potential of tin ion, this equals minus 0.14, and the standard reduction potential of silver equals positive 0.8 volt. So write the diagram of the cell. We have to distinguish between the anode half cell and the cathode half cell. So reduction potential of silver is higher, positive 0.8, higher than that of tin. So silver here refers to the cathode and tin refers to the anode. So if we want to make the diagram of this galvanic cell, we have to refer to the anode in the two oxidation states, tin SN0 solid oxidized, one diagonal line oxidized into tin positive 2 aqueous, two diagonal lines, and the cathode to oxidation state, from the higher oxidation state to the lower oxidation state, because at cathode there is a reduction. Silver positive 2, then silver 0 solid. And this is the diagram as we see here. The diagram includes the oxidation of tin into from tin 0 to tin positive 2 and the salty bridge, then the reduction process which happened to 2 silver positive ion to 2 which is reduced to 2 silver atoms. So how can you calculate the electromotive force of this cell by the values of reduction potential? It is the reduction potential of the cathode minus the reduction potential of the anode. So it is positive 0.8 minus 0.14. The electromotive force is the reduction potential of the cathode, which is silver, minus the reduction potential of anode, which is tin. So 0.8 minus 0.14, it equals 0.94. It is a positive value, as this is a galvanic cell and the oxidation reduction process here is spontaneous. So spontaneous here means positive, and positive means the reaction is spontaneous. Spontaneous means there is no outer source for the electric current. Electric current here produced spontaneously without any battery. So in this case, galvanic cell produces electric current from chemical energy. Another example, A and P are two elements, divalent elements. Their oxidation potentials are negative 0.3 volt and positive 0.7 volt respectively. So write the diagram of the galvanic cell which is formed of these two elements. We have to know that to write the diagram correctly. A, oxidation potential negative 0.3. B, divalent, oxidation potential is 0.7. So the oxidation potential of B is higher than the oxidation potential of A. So B here is the anode half cell. B here is the anode half cell or the anode electrode, and A, which has lower value of oxidation, is the cathode half cell. So to write the diagram, we have to refer to the anode, which is B, with the two oxidation state, B0 solid, one diagonal line, and B positive 2 aqueous, two diagonal lines which represent the salt bridge and the two oxidation state of A from the oxidized form to the reduced form, as the cathode half cell refers to the reduction process. So we have to write A positive 2, one diagonal line, A0 solid, A0 solid. Okay. Calculating the electromotive force of this cell includes the summation of the oxidation reduction potential of the two half cell, the oxidation of the anode and the reduction of the cathode, or by the values of the oxidation potentials. Here the oxidation potential of the anode minus the oxidation potential of the cathode. So here the diagram P0 solid oxidized into P positive 2 aqueous, salty bridge, and the cathode A positive 2 aqueous reduced into A0 solid. And here the electromotive force expressed in the oxidation potential can be calculated by the oxidation potential of the anode, which is B, minus the oxidation potential of cathode. 0.7 minus 0.3 equals 1 volt. So the question here, would this cell produces electric current spontaneously or not, or produces electric current or not? Here we see the value of the electromotive force positive. So the positive value here means that the oxidation reduction potential is here spontaneous, so it produces electric current. Okay. Another question, calculating the electromotive force of the galvanic cell. Electrochemical cell is represented by the cell diagram. Anode, which is nickel, two anode atoms oxidized into three nickel atoms oxidized into 3 nickel ions, and the cathode here 2 ions of gold reduced to 2 atoms of gold. So what is this value? It is oxidation or reduction. We have to look at the equation. Nickel here oxidized into nickel positive 2, so the potential here refers to the oxidation potential. So the nickel oxidation potential is positive 0.25. Here gold is oxidized, so this refers to the oxidation potential of gold, which is negative or minus 1.5 volt. So what is the value of the electromotive force of this cell? The electromotive force of this cell is can be calculated by the oxidation potential of the anode minus the oxidation potential of the cathode. So it is 0.25 minus 1.5, 1.5, okay, the oxidation potential of the cathode. So it is the oxidation potential of the anode minus the oxidation potential of the cathode. Positive 0.25 minus 1.5, it equals positive 1.75. So the correct answer here is C. Another example, in the opposite figure, the potential of silver and the potential of copper. But what is the potential of silver? Is it an oxidation potential or reduction potential? Here the equation refers to that silver is reduced by 1 electron from silver ion to silver atom, zero solid. So this is a reduction potential, and also here it is a reduction potential of copper. So how can we calculate the electromotive force? By the values of reduction potentials. Here the value of silver, reduction of silver, is higher than the reduction value of copper. So the cathode is silver and the anode is copper. So how can we calculate the electromotive force of the cell by the values, by indication of the values of the reduction potentials? It is the reduction potential of the cathode minus the reduction potential of the anode, and here it is A, the reduction potential of the cathode minus the reduction potential of the anode. So at this point we will finish this session. Thank you all. Your advices, your comments are very welcomed. Stay with us, we'll explain everything. Thank you.